doing? Okay.
Yep, and we can see yours now, so you should be all set.
All right. Okay. Well, there we are, back on slide 1. Thank you, everybody, for your time today. Hopefully, what we've got to tell you today will be informative and help you close underground storage tank sites. So we're going to talk about LNAPL conceptual site models and how we can use those in figuring out what sort of actions to take to move these UST sites to closure, and then dig into some specifics on in situ chemical treatment for petroleum hydrocarbons. So agenda pretty simple. I'm going to start out with an overview of what happens when LNAPL is released. So product is released from an underground storage tank or piping or dispensers. I'm going to describe what happens to that LNAPL in the subsurface. And then move into the LNAPL conceptual site model, starting out with what we should know about that LNAPL release, and then using the LNAPL conceptual site model to decide what we should do about that release. Then we'll start talking about some of those things we might do. So alternatives to pumping or bailing LNAPL out of wells, what we call phase change technologies. And I'll certainly explain a lot more about that. And then Jeff's going to talk about in situ chemical oxidation, in situ chemical treatment, and why we see rebound so often when we use that remedial technology. And then I'll come back and discuss a few other phase change alternatives to ISCO. So what I want to start out with is framing up the overall problem and asking the questions, what's wrong with the old approach to LNAPL sites, and is there a better approach that we can use? So the old approach to assessing LNAPL risk started out with drilling some wells at say, a service station and seeing if there was LNAPL in those wells, free product. And if there was LNAPL in the wells, we would try to remove it. And the conceptual model was that as long as there was LNAPL in the wells, there was a risk that that LNAPL was going to continue moving to new wells, continue expanding its overall footprint. So you can see there in the leftmost panel, we've got this situation, probably a fairly recent release. There's LNAPL in the wells. You can see that the little red bars there in my schematic wells. And maybe early on I can recover quite a bit of LNAPL from those wells. And there might be situations, there might be eventualities where we have a well that didn't have LNAPL in it, and all of a sudden it has new LNAPL in it. We know that LNAPL, that's evidence that that LNAPL is moving. In what will become the middle panel here, the right panel now, we also would have situations maybe further in time away from the release. Maybe the release happened 5, 10 years ago. We still have LNAPL in some wells, but at other wells, we've never seen LNAPL occur in them. They've been there for several years. But still, the way we thought about it was there's LNAPL in the wells. We need to get it out because we need to minimize the risk that that LNAPL is going to move and expand the overall footprint of the LNAPL zone. So as long as there was LNAPL in wells, we really focused on trying to stop that LNAPL from moving. Whether on the left panel we could pump a lot of LNAPL out of the wells, or on the right panel maybe we could just pump a little bit. Maybe you could just get a bailer full every week or something. And then there were some sites where we never saw LNAPL, and maybe there were other sites where LNAPL stopped occurring in wells. Whether that was through natural degradation or the efforts of product recovery is a bit of a question. At those sites now, this rightmost panel, what we focused on was the dissolved phase risk. But we didn't really focus on the dissolved phase risk until we got rid of the LNAPL. And the belief was that when we had the dissolved phase risk and no evidence of LNAPL in the wells, that there was no LNAPL in the system. There was no LNAPL in the ground. We were just talking about soil contamination. I put big quotes around that. So overall, the way we assessed the risk at these sites was by looking to see how much LNAPL there was in the well. And then we'd think about the dissolved phase risk too, if it was still present after we got rid of the LNAPL. So about 10 years ago, ITRC put out formed a team to look at LNAPL, and that was based on some work that had been done in the preceding 4 or 5 years, and really pushing a new way to think about LNAPL sites, more science-based, looking at the risks that were present for each of these scenarios. So again, we start here on the leftmost panel with a fairly new release. We've got what we'll call unstable LNAPL, and that LNAPL is above the water table, it's below the water table, it's mixed in with the soil and soil vapor. We'll talk about that more in a minute. And then there's LNAPL in wells, and that LNAPL body, like I show there with the arrow along the water table. That LNAPL body is moving. It's expanding. It's going to occur in new wells as we put them out there. But what we want to think about here is that we're not only concerned about the risk of that LNAPL migrating, that there's already a composition risk occurring here. There's benzene in groundwater next to that LNAPL. And then on the other side of this line, now we've separated this from separated the right two panels from the left one, and the LNAPL is stable in the middle panel. There's still some LNAPL in wells, but the LNAPL body overall isn't moving. And then on the rightmost panel, there's residual LNAPL. Okay, so there's still oil in the pores of the soil, but it doesn't flow into wells. It's still creating, say, a benzene groundwater plume. So really, on these right two panels, the thing we're most concerned with is the composition risk. So there isn't a migration risk anymore. There's a composition risk that we might want to solve. So now we want to look at these risks all together. So we're going to look at the risk of LNAPL instability or migration and the risk due to the LNAPL composition. So using this kind of new approach, let's start stepping into what's going on at sites and the value of free product removal. So you've got that stable LNAPL body from the middle panel before. You've got LNAPL in wells. The LNAPL body isn't expanding, so there's no migration risk. When does free product removal make sense? Well, it makes sense when we can change the mass of LNAPL that's in the ground, whether or not we can change the thickness of LNAPL in wells. And there are a lot of situations where LNAPL thickness is driven by factors other than the mass of LNAPL in the ground. What we don't want to do is recover LNAPL if we can't change the mass of LNAPL in the ground, even if we can change the thickness of the LNAPL in the wells. So when you're thinking about free product removal, the question you want to ask yourself is, will LNAPL recovery significantly change that LNAPL mass? And then, what are the alternatives to LNAPL recovery? How are we going to avoid performing LNAPL recovery when it's not an effective remedial method? So about a year ago, I gave a webinar for NUIPIC and talked about LNAPL stability, LNAPL recoverability, and natural source stone depletion. And now I want to focus on what's the composition risk and how do we address that. So let's start out with the basic science of what's going on when there's an LNAPL release. So we start here at time 1. Let's see if we can pull up an arrow here. Or even better, the laser pointer. So here we are at time 1. The LNAPL here is shown in red, grading from red to green in these set of panels. At time 1, we've got an LNAPL release from, say, an underground storage tank. It migrates down through the vadose zone, just due to gravity, and gets to the water table where it starts to spread laterally. And the reason it spreads laterally is because at the point it reaches the water table, there's some pressure, some LNAPL head, forcing the LNAPL downward, and resisting that downward migration into the saturated soil is soil pore resistance and the buoyancy of the LNAPL. Remember, LNAPL is lighter than water, non-aqueous phase liquid. So there's some buoyancy to that LNAPL. So then at time 2, when there's still enough LNAPL head to overcome that soil pore resistance and the buoyancy, the LNAPL continues to migrate downward below the water table, but it also spreads out laterally because as you get more and more resistance, some of that LNAPL head is translated laterally and the LNAPL body spreads. At time 3, the spread starts to slow as the LNAPL saturation reduces. So in times 1 and 2, we had very high LNAPL saturation, so there was a lot of LNAPL in the soil pores. As time goes on, and say this release is stopped here, so we're not contributing to the massive LNAPL in the ground anymore. The spread of the LNAPL slows, and the saturation of the LNAPL decreases. So first you have drainage of the LNAPL that was in the vadose zone, so that saturation reduces. And then as you get to the edges of the LNAPL body, that saturation is smaller also. And finally, on time 4, you reach some stable configuration of the LNAPL body. You get down to what's called residual saturation. All of the drainable LNAPL has drained out of the vadose zone, but there's some residual oil, gasoline, diesel, whatever, that's left in the pore space in the vadose zone. And then also there's a rind of residual level saturation LNAPL around a higher saturation core of the LNAPL body. So if we look in detail at that stable LNAPL distribution, up here in the vadose zone, LNAPL is sharing pore space with water and air. So the water is this blue halo around the soil grains. The soil grains are what's called water wet. So the water sticks to the soil grains. The air occupies the largest pore spaces. And then in between the air and the water is the LNAPL. And in the vadose zone, it's called an intermediate wetting phase. So it exists in between the water and the air. As you get down to the capillary zone, you start closing off. You no longer have a continuous air phase, so the air can't move. But still, the water is here coating the soil grains, and the NAPL is existing in there mixed in with the water. And then you move down into the saturated zone. You get rid of all of the air. Now you've just got water and LNAPL, and the LNAPL, like the air now, is occupying the largest pore spaces. And then as you move down into this residual zone, the LNAPL saturation becomes smaller, and then outside that residual NAPL saturation zone, you get into fully water-saturated soil. So the point of all this is that the LNAPL shares the pore space with groundwater and soil vapor. When you're in the LNAPL zone, when you're within the LNAPL body, all 3 phases are present. Of course, sit down here in the saturated zone where you've just got the 2 phases present when you get rid of the air. So looking up there in the vadose, let's look a little more closely what's going on. I said that up here in the vadose, LNAPL is this intermediate wetting phase. It's in between the water that coats the soil grains and the air that's in the largest pores. So when LNAPL migrates down, any NAPL migrates down through the vadose zone, it has gravity pulling it downward. There are some capillary forces that are on it, but you can see in panel A, when you've got a homogeneous vadose zone, that NAPL just continues to migrate downward. If you look closely even on here, the researchers here have drawn some fronts on here as how the NAPL has migrated, proceeded through time as it migrates downward in the vadose zone. What's interesting is when you put a finer grained block of soil in here, because the NAPL is an intermediate wetting phase and there's some capillary tension on that NAPL, the NAPL will get pulled into, get imbibed into a finer grained soil where there's open pore space, air-filled pore space. So it's something to think about when you have a situation where the LNAPL has distributed itself either in the vadose zone or you have large water table fluctuations, maybe going across different grain size zones, that when the LNAPL is above the water table, above the top of the capillary fringe, and it encounters a finer grained material, that LNAPL will imbibe into that fine grained material. And that could have real implications for what you're going to do to remediate that LNAPL. So similarly, when we get down into the saturated zone, one of the things we need to consider is how LNAPL affects what's called the relative permeability. So in the LNAPL zone, again, water and LNAPL are sharing pore space. And because they're sharing pore space, they are inhibiting each other's movement. And this is called relative permeability. So soils have an intrinsic permeability, and then the relative permeability, when there are two or more phases present, tells you how much that intrinsic permeability is reduced for each of these phases. So if we look over here on this diagram, this is a diagram plotting relative permeability on the y-axis versus saturation on the x-axis. Now, water saturation goes from 0 on the left to 100% on the right, and NAPL saturation goes from 0 on the right to 100% on the left. So it's just it's an axis showing how the pore space is split between the water and the NAPL. So when you have 100% water saturation, no NAPL in the pore space, the relative permeability is 1, which means if you take it times the intrinsic permeability, you still end up with the intrinsic permeability. But as you start putting NAPL into that pore space, the relative permeability drops quite rapidly for the water, because the NAPL is occupying the biggest pores, so the highest permeability portion of the pore space. So let's just look at an example here. Say we have a NAPL saturation. So that's S here is the saturation, is the percent of pore space occupied by the non-wetting phase, the LNAPL. Say that's 15%. We come over here and get about 15% LNAPL, come up to this LNAPL relative permeability curve, and here the symbol for relative permeability is this K, which is permeability, with a relative for the non-wetting phase. So we look at this red line here, look at the 15% NAPL saturation, and come over here to the relative permeability, and let's call it about 2%. So the relative permeability, even at 15% saturation, is only about 2% of the intrinsic permeability. On the other hand, if we look at the water saturation, the wetting phase saturation, and say that's 85%, right? Because we're splitting this even between the NAPL and the water. So there's nothing else in the pore space. So 85% water saturation, same point on the scale here, on the x-axis. We move up to the water relative permeability line. And that comes in, gives us a relative permeability of about, say, 26%. So just by having that NAPL, for this particular example, in the pore space, we've reduced the water permeability by a factor of 4. And I want to say that this is not a universal relative permeability curve that I'm showing here. Each soil has its own relative permeability curve. So, and there's lots of research and documentation that you can look into to figure out some characteristic relative permeabilities for different soil types, and you can also do testing to actually ascertain what those relative permeabilities are for a site-specific soil. So again, what this is going to do is within the LNAPL body, where LNAPL is in some of the pore space, just the presence of the LNAPL is going to restrict the movement of water within that LNAPL zone. So what else is going on? So you've got the LNAPL out there. It's formed a more or less stable body. Water tables move up and down. In some places a little, in some places quite a bit. So what's going on there is, here's a diagram showing how much of the pore space, again, that the saturation is occupied by these different phases. So here's the water table. Blue shows the water saturation going from 0 on the left to 1 on the right. And red shows the NAPL saturation going from 0 on the right to 1 on the left. And then this tan color is how much air is in the pore space. So above the water table and above the capillary fringe, we're going to have some air in the pore space, sharing the pore space with the NAPL and the water. So we start out with this, what's referred to as a shark fin looking distribution of NAPL saturation. And that equilibrates with some thickness of NAPL in a well. When the water table drops, so here we have the water table going from a high point down to a low point here. The NAPL drops with the water table. Remember again, there's NAPL above and below the water table. But it also leaves behind a residual saturation in the vadose zone. And this is the 3-phase residual saturation. So there's still some NAPL in the well. That this portion of the NAPL is still mobile enough that it can drain into a well. So water table comes back up a little bit. And when the water table comes back up, it leaves a higher 2-phase residual saturation in the saturated zone. So now we're losing quite a significant mass from this mobile NAPL interval. And we can see that when this is an unconfined homogeneous situation, we can see that by declining NAPL thicknesses in the well. And then if the water table continues to rise quite a bit, we may end up with a situation where all of the LNAPL is immobilized. So we've got some 3-phase residual saturation here above the water table. We've got a higher 2-phase residual saturation below the water table, and all of that LNAPL is now trapped. It can't move. It can't overcome the tension of the water holding it in those large pores. So at this point, NAPL is immobile. We will not see it in wells. But then if the water table drops again, we can remobilize some of this LNAPL. And we see that in droughts. I've seen that out here in Southern California, and I saw that the last few years with the drought out here. Got lots of calls, people saying, hey, we've got a site, we've never seen LNAPL for years and years, and suddenly there's some new LNAPL. Well, that's because our water table was dropping and exposing these submerged zones. So now we're seeing LNAPL in wells again. So here's a sand tank experiment that was performed by one of my colleagues when she was doing her master's thesis at Colorado State University. And this is a great visualization of what's going on in these diagrams that I just showed on the last slide. So here we are at a low water table condition. We've got this mobile NAPL interval here. You can see with the greener area in the porosity there. That's the LNAPL that's in that porosity. And so we've got a higher saturation there. You can see the more intense green color. But up above that, you can even see some little blebs of this green color. That's that low three-phase residual saturation up above the water table in the unsaturated zone. And here we're at the lowest water stand in this experiment, so there's really no LNAPL below this. We can see this is all this down here is clear of LNAPL. When you raise the water table, you leave behind quite a bit of LNAPL below the water table. Now we can see a lot more of these spots of intense green color below the water table, which is up here now. So this corresponds to this interval in the schematic where we have this two-phase residual saturation. Here is the mobile NAPL interval, the NAPL that is able to drain into this well and express itself there. And then above that, a little bit of vadose zone with some three-phase residual saturation. So linking this back to the relative permeability we were talking about earlier, down here, remember this NAPL is residual. It can't move. So here, the non-wetting phase, the NAPL relative permeability is 0. And remember that also restricts the ability of the water to move, so the water relative permeability is less than 1. At this point, I haven't characterized it, so we don't know what it is. Up here in the mobile NAPL interval, we have a non-wetting phase, a NAPL relative permeability that is greater than 0. That LNAPL can move. We know it can move because it's drained into this well. And then also similarly there's LNAPL in the pores, so it's restricting the water mobility. So that water relative permeability is less than 1. So as we've smeared that LNAPL out, that also helps stabilize the LNAPL body because we're using the mass of LNAPL that was released and spreading it over a larger vertical interval. So there's less NAPL to form a head to push that NAPL more broadly out. As the LNAPL starts to weather, almost immediately, we have what's called natural source zone depletion. That's this NSCD. So the first thing that's doing is that's just weathering the NAPL, and there are a lot of processes that's going on. Again, I'd refer you back to my webinar last year. There's volatilization and methanogenic biodegradation and other biodegradation that's happening in the saturated zone, and all of that's working together to deplete the mass of LNAPL that's in the ground very slowly. But it's happening. And the other thing that's doing is, remember we had that stable LNAPL body that I described a few slides ago, where there's still LNAPL that is in the core of the LNAPL body, still mobile LNAPL, and that mobile LNAPL can drain into the wells. That's why we know it's mobile. So if there's some gradient on that mobile LNAPL, it can move from the center of these LNAPL bodies toward the edge. But as it moves toward the edge, it's being depleted by natural source zone depletion. And as that LNAPL body ages, the natural source zone depletion will also start to cause the leading edge of the LNAPL body to recede. So natural source zone depletion is acting both to reduce the mass of LNAPL over fairly long time frames, and it's acting to stabilize the LNAPL body. So we can think of this a lot like a glacier, right? We've got a lot of snow up here at the head of the glacier. It's moving down this valley. But as it gets further and further down, there's a bunch of evaporation and melting that's happening, depleting the amount of snow and ice. So that's the natural depletion of this glacier. And what the result is that even if you have a lot of snow being deposited up here at the head of the glacier, the toe of the glacier doesn't move, right? And in fact, in this case, we can see the terminal moraines down here past the end of the glacier, indicating some past larger extent of this glacier. So the natural depletion of this glacier is actually moving the glacier back up the valley. So, you know, that's really a good analogy for what happens over the very long time frame to petroleum hydrocarbon LNAPL body. So that's what happens when you've got LNAPL, when you release LNAPL to the subsurface in the absence of any other remedial efforts. So that starts to give us an idea of what the science is that we're dealing with and what we need to do to accelerate the pace of that cleanup if necessary. So what we want to do is form what's called an LNAPL conceptual site model so that we have a good idea of what's happening around that LNAPL zone. So what is an LCSM? It's the LNAPL conceptual site model, and we want to differentiate it from just your regular conceptual site model. So here's the overall conceptual site model. It's this big picture. You've got a receptor here, maybe the vapor intrusion. You've got a receptor over here for drinking water. You've got pathways through the groundwater, pathways through the vapor phase. This is your and then you've got your source zone here, and that's your overall CSM. When we're looking at an LCSM, what we really want to focus on is just this source zone. We really want to understand the architecture and chemistry and physics going on in that source zone, and that's going to help us make choices whether or not to remediate that source zone and how to remediate that source zone. So here's a big complex flow diagram that starts to tell us how we're going to use our LCSM to evaluate different alternatives for remediating LNAPL sites. So we start here, either you've got a new site and you've got some initial investigation, or an old site and you're reviewing old site data. We come in here and we start out with an initial take on our LCSM. And that's also going to involve formulating a CSM for our site. And what that's going to do is help us understand what concerns we have about this site. What are the risks present at this site? What other concerns do we have about LNAPL present at this site? And then you keep moving through here, and you come back to the LCSM when you decide that you've got a concern that requires you to take action. And you're going to need to come in and make a more detailed assessment of your LCSM, maybe do some more investigation to really understand what the best remedy or control is going to be. And then you're going to think about how you're going to design that remedy or control, and you're going to need to come back to the LCSM and maybe gather even more data to beef up that LCSM so you really have a good basis for design and then a basis for evaluating performance. In the end, that's going to get you to no further action. The other thing I want to point out here is that at basically any step of the game here, we can decide that that LCSM that we're working from isn't sufficient. And we need to go back a step and ask critical questions about what the decisions we're making based on the LCSM. And perhaps if you get to you can get to a point where you may get all the way to the end of operating a remedy and decide that it's not doing what you wanted to do, and you may end up having to go all the way back to your initial LCSM. And that's okay, because LCSM should be an iterative element of your project. You should always be willing to come back, change your LCSM, change the way you're thinking about the LNAPL site. So what What you don't want to do is get caught in the trap of thinking your site is simple, you know what's going on, you don't need to do investigation, you don't need to look at the data closely. You know, I've worked on many sites, I know what I'm doing. I hear that a lot, or this is a really simple site. It shouldn't take a lot of thought and effort. And the LCSM doesn't have to take a lot of thought and effort. It can be a relatively simple document, a living document that you keep that just records what all your information is for the site. So, we really don't want to get caught in this trap where we think we know what's going on, we have a loose idea of what the problem is, we know what remedy we're gonna choose, we just choose it, and then we operate it, we install it and operate it, and we think that that's going to get us to no further action. And at some sites, let's be honest, it has. But I think we're getting to a point now where the sites that are left are more complicated. So the reality we're seeing now is we operate a remedy and we decide that was the wrong one. We have to go back and choose another remedy from our quiver of remedies. And there's a lot of evidence for this. So we can look at the backlog for UST sites, and that backlog has been diminishing, and that's good. But the rate at which that backlog has been diminishing has also been diminishing. So we're not closing as many sites. We didn't close as many sites in 2016 as we did back in the early 2000s, or even the mid and late 2000s. And this is because the balance of the caseload is tipping toward these older cases that have been around for a long time and are probably more complex sites. So you can see here again, this is that 2011 backlog study. At that time, there were a lot of sites here. Probably almost 70%, more than 70% of the sites were more than 10 years old. And then you look at that time, the closure rate for those sites, and they were quite small. So 70% of the sites are more than 10 years old, but only about 16, 17% of those sites were being closed. So there's a real discrepancy there. Now that's over the entire UST program life cycle. So we can even look here at kind of the trends over time. So this was the distribution of open cases in 11 states, and 78% of those cases were groundwater cases, and those are probably the most complex cases. But you can see here that the percentage of cases that were being closed that were groundwater cases fell below that 78% threshold, even in 2008, and doing much better in 2008 than we were in 1990. So overall, what this has contributed to is we were able to close the simple sites relatively quickly without doing a whole lot of development of the LCSM, using some basic instincts. But over time, that standard of practice has led to us having a lot of more complex sites that could really benefit from some clear thinking about how to get to endpoints. And this is just reinforced by a study that was done a few years back that looked at remediation of LNAPL sites where groundwater was impacted. And what it looked at was the rate of cleanup of these sites. So you can see here, so three different constituents: benzene, MTB, and TVA. And what we're looking at here is the half-life of groundwater concentration reduction. So for the benzene sites, if you just let them go all on their own, concentrations would reduce by half every 3-ish years. For MTBE and benzene, we're talking, 3-ish and less than 2 years. So if you apply a groundwater remedy only, and then that could be anything from air sparging to in situ chemical oxidation, that there was no discrimination in this study. There was a little bit of improvement in the half-life for benzene, but no improvement in the half-life for MTBE and TEA. Interestingly, when you added LNAPL recovery either on its own or LNAPL recovery in combination with a groundwater remedy, the half-life increased. So we're doing LNAPL recovery, and it's taking longer to clean up these sites, which is a bit counterintuitive, but it says that the value of that NAPL recovery or the NAPL recovery combined with a groundwater remedy doesn't come out of the statistics, that there doesn't appear to be a value. And I think that can be linked back to the conceptual site models, the LNAPL conceptual site model, understanding the source zone so you understand how you're trying to remediate the source zone. So let's start in with building an LNAPL conceptual site model. We want to iterate through it. So we'll start with the initial LCSM and establishing what our concerns are. And then, like I said, when we establish our concerns, we want to look back. We want to say, was the LCSM sufficient to really determine that those were the concerns? And if it isn't, go back and improve your initial LCSM. If it is, then you can decide whether or not a remedy or a control is required. So I apologize for the big text slide here, but these are a bunch of questions you want to think about when you're developing that initial LCSM. You want to ask yourself, where is that LNAPL zone? Where is the mobile LNAPL? Where is the residual LNAPL? And not only do I know horizontally where it is, but do I know vertically where it is? If there's been a lot of water table movement up and down, then I want to go down deep enough to find the bottom of that LNAPL zone. And as part of this, I want to ask, is that LNAPL body stable? Do I know that the LNAPL footprint is not expanding? That'll give me reassurance that migration isn't an issue I need to address, and that the risks that remain are really connected to the composition of the LNAPL and whether it's driving vapor phase or dissolved phase plumes. And that's another question down here. Do we expect there to be dissolved or vapor issues? Is it a gasoline plume? Is it a diesel plume? They can differ a lot about how much the composition is going to drive these other phases of contamination. Do we have soil or soil vapor or groundwater that exceeds criteria? Are there pathways that are complete to the receptors? And then, some more detailed questions that go back to that initial discussion I had. Is there LNAPL in wells, and is that LNAPL recoverable? So can we make a difference in the mass of LNAPL in the ground by pumping LNAPL out of wells? And last, is there something about the stratigraphy that's going to potentially complicate what's going on as I try to investigate the distribution of LNAPL, and then in the future think about how I might mitigate it? Maybe there are preferential pathways that exist. So we can use the answers to those questions to start to develop what the LNAPL concerns are for a site. So here we've got a site, leaking tank, LNAPL that's reached the water table. It's distributed above and below the water table. So maybe there's an emergency condition where we've got vapor accumulation in confined spaces causing explosive conditions. But if you get past that, you can really start to dig into the details of the conceptual model. Is there a dissolved phase that's heading toward a drinking water well? Are there vapor phases that are heading to a receptor at the ground surface, either from the LNAPL body itself or from petroleum hydrocarbon constituents in the groundwater? And then back to the LNAPL body itself. Is the LNAPL body stable or not? Is it potentially mobile? And then also, is there LNAPL in wells? And again, is that LNAPL recoverable from wells? And what we do is we separate all of these concerns into bins. LNAPL migration, when we're concerned about that LNAPL moving somewhere. And maybe that migration concern could include migration to surface water, where we might have sheens, or migration to other underground spaces where the LNAPL is either more accessible to receptors or can migrate very quickly. Then we've got LNAPL saturation concerns, and that's where, back here in the NAPL zone, we want to reduce the saturation of the NAPL, reduce the mass of the NAPL. And finally, there are the LNAPL composition concerns. Those are the concerns that the LNAPL is an ongoing source to groundwater or soil vapor. So then once we've figured out what our concerns are, we decide what we need to do to mitigate those concerns. So what we want to do is establish goals for the site. What goals do we need to accomplish to mitigate the concerns and risks at the site? And then we come over, and based on what we know our concerns are they saturation concerns, are they composition concerns, we go in and ask ourselves, what do we need to improve about our knowledge of the site? How do we need to improve the LCSM so that we can select the right kind of remedy to accomplish our goals? Again, you come over here, always ask yourself the question, was my LCSM sufficient to really make that decision about what remedy or control I'm going to use? If not, I'm going to step back and I'm going to look at whether remedies or controls are required and what the concerns are. So here's a graph showing the range of LNAPL saturation here. So I've got a lot high NAPL saturation over here on the right, low NAPL saturation over here on the left, and this is bounded by this variable we call the saturation concentration, and that's the soil concentration above which NAPL must be present in the pore space. So up here at the highest saturation, we have mobile NAPL, and that NAPL might be migrating. We're going to see those highest saturations really only after, immediately after release, when that LNAPL body is expanding. When we have migrating LNAPL again, we're going to think about remedial technologies that give us mass control. So they're going to control the mass from migrating. But maybe the NAPL is a lower saturation, or mass recovery, just pumping the NAPL, could slow migration. So at that larger saturation range, LNAPL saturation range at the high end, we've got recoverable NAPL that might be recoverable to the maximum extent practical. We're going to use mass recovery technologies. And then finally, the type of technologies that cover the entire breadth of NAPL saturations, from the highest mobility saturations all the way down to the lowest residual saturations, are phase change technologies, because they're dealing with the composition of the LNAPL, whether or not it's mobile or moving. So what we want to do is think about what our goals are for the site and respond to the actual LNAPL risk. So we're thinking about the LCSM for selecting a remedy. One of the first questions we want to ask is, maybe we have a bunch of different goals for this site, or concerns, but what we want to do is figure out which concern is going to be going to drive the most conservative objective. What concern is going to require us to deplete the most LNAPL, and use that to start to think about what remedies we might choose. Then we want to get a more detailed idea of where the LNAPL is above and below the water table. How permeable is the soil that the LNAPL is in? How heterogeneous is that permeability? How about the LNAPL itself? How volatile is the LNAPL? Are there technologies that you can use that can volatilize a significant portion of the LNAPL? So even, not only how volatile is the LNAPL, but what fraction is volatile. And then also, biodegradation is a huge factor around NAPL. We know that from looking at the rate of natural source zone depletion. So is there something we can do to enhance that biodegradation, make it go faster? So here are a bunch of LNAPL remedial technologies pulled into these different groups. So we have mass control technologies, mass recovery technologies, and phase change technologies. And you can see a lot of common technologies in there, a lot of uncommon technologies, maybe some that have only been used a few times. One thing to know about these categories is they are not hard and fast. All of these technologies have multiple ways that their physics and chemistry act on the LNAPL. So in particular, there are a number of technologies here like bioslurping or multi-phase extraction that not only pump LNAPL out of wells, but they also induce phase change on the NAPL. Similarly, there are some of these technologies, particularly the heating technologies in the phase change column over here, that also are going to enhance mass recovery. So finally, we get down to the actual implementation of whatever remedy or control we're going to put in place. So we want to really improve the LCSM where we're going to implement that remedy or control. So we're at a design and performance LCSM stage. We're going to establish specific objectives for the remedy or control. We're going to establish how we're going to measure progress towards those objectives. And then we're going to design and operate that remedy or control and measure our progress toward that endpoint so we know when we get to the endpoint that we have for that particular technology. And then hopefully, if we've followed this along and we've developed a good LCSM, maybe we've been willing to loop back a couple of times, we're going to meet those objectives and goals, and we're going to get to no further action. So when we're improving the LCSM for designing a remedy and evaluating its performance, we really want to ask very clear questions about what is that technology going to change about the LNAPL? How am I going to demonstrate that those changes are happening in the LNAPL body? And what are the conditions that I want to achieve at the end of that remediation? Or also, another way to phrase that is, what do I think that this remedial technology can reasonably do? And that links into this next question here. What cost of incremental change is going to be too high as I get toward the tail end of operating a remedial technology? Would there be another follow-on technology that I could use that over its life cycle would cost less to get me all the way to my overall goals for a site? And when I'm establishing these remedial objectives and metrics, I want to use the acronym called SMART, right? I want to be specific about those objectives and metrics, know exactly what I'm talking about. They must be measurable, okay? I have to be able to measure what I'm doing. I want to know that I can actually make those measurements, and when I'm talking about objectives, that I can get to those objectives with that remedial technology. Those objectives and metrics should be relevant, again, to the cleanup that I want to get to with that technology. And they need to be timely. I need to be able to make those measurements repeatedly in a timely manner so that I can understand progress toward my endpoint. So LNAPL recovery is something we do at a lot of sites, whether it's a skimmer system, whether it's a multi-phase extraction system, or it's monthly, quarterly bailing or back truck events. But I think I've shown that sometimes that isn't effective, that isn't going to get us to the overall goal we want to for a site. So rather than continuing to do those recovery efforts, let's think ahead to what else could I do at that site. So this is where that we want to really start to think about that composition risk and focus on it. Even here in the situation where we have unstable LNAPL, if the composition risk is what's going to be the biggest risk at the site, then let's focus on that. And certainly when we get here at the stable NAPL and the residual NAPL, really focus in on how does the composition of the NAPL present risk to the environment. You know, is it driving a dissolved phase plume? Is it driving a vapor phase plume? Are there receptors? And the reason is that when you have composition risks, phase change is the most effective. So here's a thought experiment. So we have a base case where we're just going to let natural depletion take care of this. And that gives us a relative time of 1, and over the life of this LNAPL body, it's going to give a groundwater concentration, a relative groundwater concentration of 1, right? So if I reduce the LNAPL mass by 50% vertically, so I'm going to cut out the top half of that LNAPL body that's submerged below the water table, but had to leave some of it because it was too deep. Then I look at a monitoring well here that's screened over that entire LNAPL body. And case B here, because I've got mixing and dilution happening, I'm going to reduce that groundwater concentration by half, but I'm not going to change the overall time of depletion. If I go to case C here and say I'm able to dig out half the LNAPL body, but half of it's underneath the building and I can't get to it, well, then I've got incident groundwater flow here and the electron acceptors that come with it, and that is going to reduce the time that it takes natural depletion to take care of this LNAPL body, but it's not going to change the concentration. So then if I can pump, say I can make a meaningful change in the mass of LNAPL in the ground by pumping LNAPL out of wells, then I'm going to reduce that overall mass in the ground. The LNAPL saturation is going to be reduced by 20%. Again, I'm not going to change the concentration on that compliance well, but I will change the overall time that it's going to take for natural depletion to remediate the site. Lastly, if I can do something to change the concentration of a particular constituent of concern in the LNAPL, say I reduce that constituent by 80%, the concentration in the LNAPL of that constituent by 80%, then because of Raoult's law, I'm going to reduce the concentration of that COC in the groundwater by 80%. And say that constituent was about 5% of the overall LNAPL, then I'm going to reduce the time too. The time is going to go down by a small factor. So this really points out the benefit of thinking about the composition of the LNAPL and how we can change the composition of the LNAPL to get rid of the risk-driving constituents. So here's another quick look at the same sort of problem. Here's LNAPL saturation. If I reduce the LNAPL saturation by half, it's not going to change, but that LNAPL has benzene in it that has an equilibrium concentration of about 11 milligrams per liter. Just by reducing by half the amount of LNAPL in the ground, I'm not going to change that concentration at all. If, on the other hand, I reduce the concentration of benzene in the LNAPL by 50% and hardly change the saturation at all, I've changed the concentration of benzene in the groundwater. So, and that brings us to this window where phase change technologies, the ones that change the composition of the LNAPL by moving some of those constituents from the LNAPL phase into a dissolved or vapor phase, phase change technologies can act over this large window of LNAPL saturation and LNAPL conditions. So just because you've got LNAPL in wells, don't think that you can't move straight to phase change technologies. So again, here we are. These are the phase change technologies that are commonly and sometimes uncommonly used for LNAPLs. So including some of these that are more traditionally thought of as mass recovery, as technologies you'd use for pumping LNAPL out of wells. Know that they also, like I said before, do remediation through phase change of the LNAPL. And so next up, we're going to talk more about ISCO. You know, some of the pros about ISCO are we can inject into existing wells. The injections take short duration. We really don't have any ongoing O&M, operation and maintenance of that injection system, because we can inject it and then drive away. And but what are the downsides of that? I'm going to let Jeff step in here and talk about some of that. So we drag the control over to you, Jeff.
Yeah, and Rick, before you guys transition, I did have a question if it's a good time.
Yeah, sorry, this would be a good time to pause and take a question.
Yeah, so a friendly reminder to the audience, I did receive one really good question, but all of you out there listening, feel free to use the chat function in the Q&A. You can send a question my way at any time, and we'll work to get that answered. But the question here, I believe it's regarding the slide 21, which was about submerged NAPL experiment. So the question is, I think you said that the LNAPL is trapped and water can't move when the water table rises due to permeability. And so by this example, does this mean you wouldn't expect to see dissolved contamination spreading?
No, so I didn't say that the water can't move. So the LNAPL can't move when it's trapped below the water table because it's trapped by the water. But the water still has a relative permeability that's greater than 0. So the water can move through that LNAPL zone, but it moves at a slower rate than it would if there was no LNAPL present, and no LNAPL impeding its progress. So that goes back to that example I had a slide or two before that, where the water relative permeability was reduced from 1 down to by about a factor of 4, down to about 26% by 15% saturation of LNAPL.
Okay, and whoever sent that, feel free to just send me a follow-up if that you had another question to piggyback on. But that's it for now. Thanks, Rick.
All right, thanks.
Thank you, Rick. And can you hear me, Drew?
Yes.
All right. That was an awesome talk, Rick. Thank you so much. And when we start to talk through some of the applicabilities of chemical treatment, it's going to be really important to keep in mind the concepts that Rick was talking about, because it further exacerbates the complication of what we're trying to implement with chemical treatment. Before I get too far into it, the evaluation of chemical treatment with respect to LNAPL sources, petroleum hydrocarbons, and really remediation in general is a question that we get a lot. And we had several slides, several case studies, and several third-party reviews that culminated into one of the topics that the late Dr. Sutherson was an editor-in-chief for Groundwater Monitoring Advances in Remediation Solutions column. So if you're interested, if any of the topics that I talk about specifically in the next 20 to 40 minutes, say, are really inspiring and you want to learn more about it, I'd recommend starting at this column, which is in the winter of 2017 edition of Groundwater Monitoring and Remediation, and the sources therein that we referenced. And then I wanted to give a nod to Dr. Sutherson, who passed quite suddenly in February of 2017. He was a personal mentor to me, very impactful in the field, and he will be missed. So to get started with the two objectives of what I would like to cover in this segment of the webinar is really to define the site characteristics that present those challenges to chemical treatment. A lot of it is what Rick was talking about. We're going to make it more specific to chemical treatment. And then discuss some of the design considerations to focus on managing that contaminant rebound or understanding it. And when we get a lot of requests of, hey, will you review this site? We implemented ISCO and it failed. I find more times than not that it's not so much that the chemistry failed. The chemistry is pretty well accepted. It's the application was off. So it's a calibration of expectations. Will one chemical injection fix your LNAPL problem? Probably not. But could a series of chemical injections help on that NAPL composition part that Rick was talking about? That's more probable. To run through the agenda of what we want to talk through today, we're going to identify chemical treatment, define some of the different types, talk through what causes that bounce, and then the next two will really be to define that sweet spot and talk about some of the design considerations that go into maximizing the effectiveness of chemical treatment, and then with a summary. So it'll be a little qualitative and conceptual up front, and then it'll get more detailed with quantitative case studies and the like. So on this slide, we present the classic arrangement of the electrochemical potential of well-known geochemical parameters arranged in a tower orientation. I think a lot of us have seen this before, the electron tower of connecting highly oxidized species to more reduced species. And it's relevant because that's what chemical treatment is. It's essentially a manipulation of the oxidation reduction potential of those contaminants to reduce the associated mobility and or toxicity. Specifically to LNAPL remediation and petroleum hydrocarbons, it's mineralizing those hydrocarbons to carbon dioxide. These aren't new technologies. They've been around for decades in the municipal water and mining industries, and they've always been implemented from an ex situ standpoint where you have a tank and you can turn a knob and that'll change your reagent influent to your mixed tank, and that can change your effluent within minutes to hours. But when you add the site-specific hydrogeology, geochemistry, nature and extent of contaminants that we're targeting, you have to calibrate the expectations of what chemical treatment can achieve. The chemical treatment success is really predicated on bringing the chemical reagent in contact with the COCs and allowing enough time to facilitate those reactions. Now, that can be really difficult because the chemistry is typically characterized by fast kinetics and short residence times. So some of the available treatments that we'll talk about are chemical reduction and chemical oxidation. This teeter-totter is slightly weighed more towards chemical oxidation because that's what I'm going to talk about today, and arguably the focus of industry since the 90s has been more on chemical oxidation. But chemical reduction is gaining attention, has been. We've seen it with the rise of zero-valent iron over the last decade or so, and we fully expect there to be chemical reduction applicability with respect to emerging contaminants, such as poly and perfluoroalkyl substances, which we're all paying close attention to. But from a chemical reduction perspective, it's really an iron and sulfur game. Different chemistries that manipulate those two elements. You can get some more advanced reductant radicals, but generally it's an iron and sulfur game. On the ISCO side, we've got our stoichiometric oxidant, which is permanganate, which is a direct oxidation, a cleaving mechanism, if you will, which struggles more towards the aromatic compounds that we commonly find at petroleum hydrocarbon sites. So I'm not going to spend a whole lot of time on permanganate. I'm going to focus the majority of the discussion on these advanced oxidation processes, the chemistries that result in radical propagation, so ozone, catalyzed hydrogen peroxide, and persulfate, catalyzed hydrogen peroxide, commonly referred to as fentans. And you'll notice that percarbonate chemistry is not specifically called out here. And there are commercially available products that are specifically referencing percarbonate radicals, but it's really an alkaline activated form of catalyzed hydrogen peroxide. So it's kind of captured under that umbrella. So on this slide, we previously mentioned that ozone, catalyzed hydrogen peroxide, and persulfate are really the most applicable oxidant for petroleum hydrocarbons. So, and here I say that persulfate is really the one that seems to be the best fit based on the reviews that we've done and applicability studies. It's not necessarily an endorsement of the chemistry. It's just looking at a comparative assessment of the oxidant persistence. So if we populate this slide, which will look at different persistence of chemistries in situ, so the colored bars correspond to travel distances where we would expect the injected oxidant chemistry to be degraded to 10%. And we assume a groundwater velocity of about 0.3 meters per day and pseudo first order kinetics. So if you take the rate constant that was manipulated out of all these different reference studies, and you apply that to the first order, pseudo first order rate concentration calculation, this is what you would ultimately get. You come up with a time, that time on a groundwater velocity equals a distance down gradient. So it presents a comparative representation of the length of time these oxidants would be expected to be in contact with dissolved COCs. Analyzing this a little bit more, we note that ozone, which has solubility and mass transfer limitations associated with it, it's soluble to about 6% by volume, and the dissolution of the air bubbles into the liquid can have an efficiency that's typically less than 5%. It's still likely to influence a reasonable ROI, which is about 10 feet or 3 meters. Catalyzed hydrogen peroxide, specifically called out in orange at the very bottom, has one of the smallest, and we've calculated that based off of over 140 lab scale and field scale studies, most of which were taken from the Segrist ISCO textbook, which is an excellent resource on ISCO and personally endorsed as probably the authority on the topic at the moment. And it's not to necessarily bash catalyzed hydrogen peroxide or say it's not applicable, but if you look at the comparative burnout of peroxide versus persulfate versus permanganate versus ozone, it's just where we would expect this to be used up faster. The reaction kinetics are quicker. It's more reactive. Some of the other different variations of activation chemistries available with persulfate, such as thermal, which is one of the more aggressive, that too results in a very short persistence. But if you can manipulate and engineer the activation chemistry, you can prolong its persistence. And it's that persistence of the chemistry that we're really going after, because that's what's going to provide for treatment capacity for the eventual and inevitable rebound. So stepping away from the chemistry for a second and just focused on complicated geology. Okay, so we've all seen some of these really cool rock faces on the side of the road that were cut for highway construction, or maybe when you're coming in on your approach for your landing, you can kind of take note of some of the braided streams and stuff like that. They're all really cool surface features, but they remind us of the complicated stratigraphy that's been deposited for millennia. And this is our reactor vessel. It's not an ex-situ tank. We can't turn a knob and just mandate oxidant to a low permeable unit. We're really at the mercy of the heterogeneities and anisotropy of these hydrogeologic systems. So looking at this a little further with a specific example of a 4-inch, 10-centimeter core, we see over this very short distance different soil grains or different heterogeneous material that's characteristically represented by various orders of magnitude hydraulic conductivities. If we look at the 10 to the -2, which is more representative of a clean sand. Now, it's not moving at the speed of sound, but comparatively, and the majority of flow is going to prefer to follow these more permeable pathways. Not to say that Usain Bolt is slow by any stretch of the imagination, but the 10 to the minus 4 centimeter per second in comparison to 10 to the minus 2 from a contaminant transport perspective is equivalent to those respective speeds and rates and corresponding percentage of the flow. And then lastly, the poor tortoise, which represents what Rick was talking about with a lot of the residual LNAPL that gets trapped and stuck in the formation. That's just sitting there as a potential source. And if you, for all intents and purposes, over a meaningful remediation lifetime, this 10 to the minus 6 might not contribute to contaminant mass flux, but it very well may contribute to contaminant mass dissolution from residual LNAPL. So if we look at those three representative hydraulic conductivities from more of a conceptual site model perspective, the mobile fraction is what's experiencing advection. That's what's driving contaminant mass flux in the aquifer, and it's ultimately where our injected reagents are going to prefer to distribute. So in a really heterogeneous system where we have 90% of groundwater movement dictated almost purely by pure advection, that's where we'll be most effective with an injection-based chemical treatment strategy. So why then would a one-off ISCO injection not be appropriate for a petroleum hydrocarbon site? Well, that's because of the other two intervals, the immobile and what we're calling the storage fraction. They represent the bulk of the contaminant mass that has kind of weathered and established an equilibrium, like Rick was talking about earlier. So the storage fraction might not be contributing to the contaminant mass flux down gradient, but it can continually diffuse into the immobile fraction. And while this immobile fraction is not completely stationary, right, it's Usain Bolt versus the speed of sound, it represents an order of magnitude less contaminant mass flux, but can certainly feed the mobile fraction with ongoing contamination. So our monitoring wells that we install, they pull water from the ground, and they ultimately give us a representation of this mobile fraction where we can access groundwater and pull it out of the wells. But the stored contaminant mass and the actual residual concentrations, it's somewhat limited, inherently limited to the heterogeneities and the anisotropy of the natural depositional system. So in the next slide, we're going to look at an example of what this might look like at a down gradient well from a source zone. In panel A, we see this invasion of contamination. And over this random 5-year period, we see a rise in contaminant concentration as a function of advection. What's also happening is that the influent concentration is establishing an equilibrium amongst those three compartments, the immobile, the mobile, and the storage. In panel B, we see the washout, which is also an advective process, in which the influent contamination has been shut off. So maybe there was an excavation or an in situ mix or some source area treatment that addressed the LNAPL mass, and we're dealing with the LNAPL composition phase. So the mobile fraction is diluted by upgrading impacted water, and we see this as a decrease in concentration, but there's also ongoing establishment of equilibrium with the storage in the immobile fraction. So once the mobile fraction has been flushed in panel C, there's a clear rate change in washout, and what we see is slow advection from the immobile fraction and diffusion from the storage fraction into the immobile and mobile fraction. So we're basically late stage harvesting stored contaminant mass that equilibrated in panels A and B. And then we hit panel D, and here's where a lot of times we'll think, well, you know, it's relatively low concentration, single digits to tens of micrograms per liter. It's been sustained for a couple years. Why not look at a really aggressive ISCO injection and see if we can wipe it out? And as we'll see in coming slides, the drastic shift in geochemistry that's associated with a chemical treatment can upset the apple cart of equilibrium. And you facilitate access to stored mass in the storage fraction just by changing the geochemistry so dramatically that your concentrations can rebound to higher levels that you hadn't seen in several years. And that's most likely attributed to residual blobs of LNAPL that have been trapped either in the smear zone or in the interstitial particles of the aquifer. So simplifying that conceptual site model and applying it to the applicability of in-situ treatment, we can see that in the mobile fraction, which has the majority of mass flux, we can readily address this with in-situ treatment, and it's totally reasonable. And if you're dealing with a contaminant that has low solubility or low absorptive potential and high solubility, say like 1,4-dioxane, then in-situ treatment is a totally reasonable strategy, and chemical treatment is probably a really good alternative to evaluate. When the contaminant mass is largely within the immobile fraction, now our applicability of chemical treatment is being stretched, and in-situ treatment in general. We need to manage the expectations associated with what we can achieve with an in-situ treatment strategy. We might need to inject several times, not because the chemistry is ineffective, but just because we don't have access to the contaminant that has to slowly eject and diffuse from these lower permeable units. And then lastly, if we believe that from our CSM that we have a high degree of LNAPL specific to petroleum hydrocarbons trapped in the stationary fraction, we need to go into the situation understanding the reasonable limitations of what chemical treatment can accomplish. There's an incongruency in thought to think that reaction kinetics that happen on the order of minutes to hours associated with the chemistry of chemical oxidation can be applicable to residual LNAPL, which may leach or dissolve or be made available over years to decades, right? So there's a basic incongruence in thought there, and it pays to be pragmatic in an evaluation of the applicability of chemical treatment to an LNAPL source. Now, what this conceptual site model shows with the thickness of these arrows and the percentage of mass flux talks about where the contaminants are moving. But what's certainly equally important is how much of the contaminant mass remains. And a lot of that was getting at what Rick was talking about with the residual LNAPL. That cannot be understated as an important differentiator as to whether or not chemical treatment in particular is applicable. So moving out of all the complications associated with what challenges chemical treatment from our perspective, now we're going to move into defining that chemical treatment sweet spot and ultimately defining the, talking a little bit about the design parameters. So I ask that you indulge me a little bit of artistic interpretation on the strike zone metaphor for chemical treatment, but the first is delivery. And what we mean by delivery is that we're looking to distribute our reagent throughout the aquifer in as uniform manner as possible to achieve a working strength. The working strength of the reagent can be site-specific. Sometimes you can get by with a couple % of your injected concentration. Sometimes you need 20 to 30% of your injected concentration. But we need to see more than a minor bump in the field parameters with respect to our distribution. We need to see meaningful concentrations of our injected reagent. The next is contact times. Now, contact time might seem similar to distribution, bringing the reagent in contact with the contaminant, but in fact they're different because you could achieve a 20 to 30% injection concentration at your dose response well during the injection, but if that is gone within a week and you then have subsequent rebound or LNAPL mobility or enhanced dissolution that requires chemistry, this gets to the persistence issue, then you don't have an effective treatment more long-term. The third is access, and access is kind of good and bad. If you have 100% access to your source mass that is in a solid equilibrium and you upset that equilibrium with a drastic change in geochemistry or exothermic reactions that change the solubility of the LNAPL or its mobility, you might see rebound above baseline concentrations. Probably will. We have some case studies forthcoming that show that. If you don't have complete access, then your injections are sipping the reserve of contamination, and this presents a disastrous circumstance for ISCO because it's a never-ending cycle. You can continue to inject and continue to inject, and you're just going to be getting the very tip of the reserve of contaminant mass. The reason I asked for artistic interpretation, we'll assume that access was a foul tip because there's a fourth one that's can't be understated when we're considering chemical treatment with respect to petroleum hydrocarbons, and that's a flexible regulatory framework. If there's a hard line in the sand that we need to achieve MCLs of all petroleum hydrocarbons, it's ill-advised to proceed with chemical treatment. But if chemical treatment is used within the confines of a system that allows for regression analysis or low-risk closure, then it's certainly much more applicable. So now we're going to talk about some of the design parameters that influence that strike zone, and the first is optimizing the reagent and distribution. On the right there, we show a picture of a highly saline injection that we were doing where we were using continuous downhole specific conductivity measurements to confirm the volume to distribution relationship. Volume to distribution relationship is defined as the injection volume that you need to achieve a working strength solution at the targeted radius of influence from your injection well. And a lot of the chemistries associated with chemical oxidation afford the opportunity to use specific conductivity or pH or a field parameter as a surrogate. Secondly, we want to talk about the importance of treatability testing. Certainly from a chemical standpoint, the role of treatability testing is important because it gives us a sense of what we can expect geochemically at a site. There's always room to improve a design with respect to reagent dosing, so treatability can help us knock down costs associated with the implementation by leveraging our experience. We can understand the secondary water quality influences listed there. It's called out as like the buffering capacity, but when we change the geochemistry, we can open ourselves up to potential secondary water quality characteristics, and we'll talk about some of them. And then lastly, the nature and extent, and this really gets at what Rick was hitting on with the LNAPL CSM, because when we're at a petroleum hydrocarbon site, it's more likely than not that we have residual LNAPL that's trapped. And it may not be mobile, it may not be accessible, but it's likely that our chemistry can change that very quickly. LNAPL can reside above and below the water table, as Rick indicated in the smear zone, and if we go after it with really aggressive chemistry, we might change its solubility, we might change its mobility, it might show up in locations where it hadn't shown up before. we have absorbed mass there, and that's to a lesser degree and defined as really high concentrations in groundwater that's come to equilibrium with the organic component of the aquifer. And something that we can consider with nature and extent is the historical groundwater concentrations with respect to groundwater elevation. And we've got a case study coming up to talk about that as well. So venturing into some of the design parameters here, this idea of dispersion is an antiquated view of injection remediation. The idea that small volumes of high concentration will kind of lampshade out as they move down gradient has been proven time and time again to not be true. As high resolution characterization has improved and the body of tracer test data within the industry has improved, this transverse dispersivity, which would be responsible for this lampshade distribution, is just not the way that things move. So if we're going to implement an effective remedial strategy, we need to do so by injecting enough solution that we ensure overlap of our injected ROI. And while we conceptualize that they're circles, in reality they're ellipses. So there's even a greater complication to achieve that necessary overlap. This is a conceptualized graph of the equation we typically use to calculate or predict the injection volume. So volume injected is the injection volume that's shown on the left y-axis, and it's presented there per 3 meters or 10 feet of screen. Pi, radius of influence squared times the height of the screen, and the porosity is the geometric definition of the volume of a cylinder with that porosity modifier as theta m. So the ROI is your targeted radius of influence, and the height of the screen is the vertical interval you're injecting over. And what we see is that as the radius of influence increases for increasing mobile fraction, the required injection volume just to satisfy the geometric conceptual injection volume increases pretty dramatically. So as permeability increases, so does the injection volume. And what we've observed is that appropriate injection volumes are typically on the order of 1/3 of the pore volume. And the general procedure, if you have adequate budget and planned accordingly, excuse me, this optimized reagent distribution is predicted with this equation and then supported through tracer testing with dose response monitoring. So here's an example of an inefficient volume to distribution relationship. We talk a lot about, well, the permeability was too low, and there's some common sense there. If the permeability is too low and you can't inject, then you're probably not going to be able to distribute your reagent meaningfully. But we can also have it on the other way, where we have such a permeable aquifer that the cost associated with implementing chemical treatment is just not worthwhile. So on the left, we present the injection flow rate in gallons per minute and cumulative injected volume on the x-axis. And what we typically see, if we refer to this as our injection capacity, we typically see a reduction over time because it requires more pressure to achieve a higher flow rate when you're trying to displace more volume at a greater distance. But in this instance, the formation, which was characterized by coarse gravels, cobbles, and coarse sands, the concentration, or the injection flow rate, we were able to maintain it over at a pretty good clip over the entire injected volume. So we would expect this to correspond to a response in either specific conductivity, pH, persulfate, this was the sodium persulfate injection, or depth of water, as least imposing a hydraulic response. But we didn't see any response over the course of the injection at the corresponding radius of influence. So ultimately what this shows is that at this particular site, the volume to distribution relationship was inefficient, and the cost to implement ISCO meaningfully to achieve a working strength solution would be prohibitive. So at this particular site, ISCO was disqualified and an air sparge SVE system was looked at. Next, talking about the role of treatability testing. These are just highlighting some of the potential benefits of treatability testing. If we are verging on a chemistry that we're unsure of, if we're going after some emerging contaminants, or if there's questionable site geochemistry, high brackish conditions, something like that, treatability testing can be very insightful. If proof of concept is necessary, it's generally less applicable with petroleum hydrocarbons. If we need to establish the oxidant and activator dosing, which is a great way to cut costs, if we were focused on reagent requirement, when we're looking at the total and natural oxidant demand, it's always better to consider the oxidant demand with respect to contaminant treatment, not just satisfying the oxidant demand. In my experience, the oxidant demand increases with reagent strength. That's kind of a perpetual cost cycle. And then screening some secondary effects, and we've got some case studies coming up to talk about that. So this is one such case study or one such example of where secondary water quality became a concern because of an ISCO injection, or because of an ISCO application. This was discovered at the bench by a colleagues of mine, Mark Clemmer and Sean Burnell. It's a secondary effect example of chlorinated ethanes being formed while trying to oxidize chloromethanes. So the first sort of reaction to look at is these chloroethanes, hydrocarbons, naturally organic matter, or whatever, they can interact with radicals that we create as a result of injecting our pretty dramatic chemistry. So chloride is one such geochemical parameter that's present universally. It's going to be present at tens to hundreds of milligrams per liter in normal aquifers, thousands of milligrams per liter in saltwater, tidally influenced aquifers. And as it interacts with persulfate radicals or hydrogen hydroxyl radicals, it can form radical itself. And when it does and interacts with our contaminants, organic radicals are formed. Those organic radicals can then react amongst themselves, and in this particular instance, generated 1,2-dichloroethane or 1,1,2-trichloroethane, just as a result of some of the ancillary reactive chemistry. And as a note, organic molecules can enhance this process, and at this particular treatability study was looking at using iron-activated sodium persulfate, and the iron was being chelated with a weak organic acid. So we were adding an organic molecule to the process, and that was exacerbated. But it was determined at the bench, which was able to be communicated to stakeholders, and we actually used alkaline-activated persulfate, and that helped mitigate this potential. This is an example of taking lab-scale data to the field scale as more of a pilot, so kind of tiptoeing into your full-scale implementation. There was a lab treatability test that supported ambient-activated persulfate for risk-based objectives. The CSM of the site showed that we had two intervals, a B unit and an A unit. The B unit was characterized as high permeability, and the A unit was characterized as low permeability. And the data that we present here is from the B unit, where on the left axis we've plotted the normalized benzene concentration. It's been normalized to the baseline concentration. So any benzene reduction from 1 is considered a reduction in concentration. And then on the right side, we have normalized persulfate, and then normalized persulfate was normalized to the injection concentration. So we saw anywhere from 2 to 10% response over the course of almost 4 months. That's a really strong persulfate response, and it corresponded to roughly a 60% decrease in benzene in the B unit. Now, in the A unit, this disqualified ISCO as a cost-effective treatment strategy because we weren't able to distribute persulfate. You can see at the bottom there, it was 0% response over the monitoring period, and we observed a normalized increase in dissolved benzene concentration, which was likely the result of dissolution of source mass. Rick had talked a lot about the smear zone associated with LNAPL, and this is one such injection implementation which went after a smear zone, and we see this characteristically frustrating sawtooth response. So on the left axis, we present total BTEX on a logarithmic scale, and on the right y-axis, we present the groundwater elevation, which isn't shown on this particular graph just yet. The green lines represent the injections. In the first injection on the far left, we see an initial increase in concentrations, almost an order of magnitude increase post-injection. Now that can be okay if you see it after the first injection and it's the residual LNAPL that's been dissolved and you've kind of tapped into the resource and not unexpected. So 2 following injections were kind of staggered out to maximize that rebound, right? So you see the rebound, you see it come back down, you've maximized source mass recovery or source mass access, and then come back and do another injection, no change in concentration, do another. And when the concentration came back up to where it did after the first injection, it was time to take a step back and look at this data a little bit more pragmatically. And over a course of extended monitoring, almost 2 years since the third injection, we see another high, which was actually a historical high, but not the cause of any sort of injection. And if we correlate this data with the groundwater elevation, it implies that there's a relationship between the groundwater elevation and the concentrations and potential for a submerged source mass. Now we know that LNAPL is less dense than water, and typically it'll be above the water table, and certainly a potential here for it. But one explanation that we were kicking around is that every time the water table dropped, the concentrations increased. And that may just be a dilution effect. So when there's more water, there's a lower concentration. That would imply that we have more access to our source mass at these seasonal lows, but it doesn't necessarily mean that there's not blebs of LNAPL smeared across the 2 to 3 foot smear zone that we're seeing. And if we take a step back even further and look at the history of this data set, there's even more dramatic association of high water table and extreme low total BTEX concentrations. So what we take out of all of this is that ISCO is not applicable for a smear zone treatment if your goal is MCLs and if your goal is large orders of magnitude reduction. If you have an objective that is a low threat closure, or you're trying to just reduce the mobility and toxicity of available LNAPL, potentially ISCO could have a role with a source area technique that Rick will talk about a little later, but certainly not by itself to get MCLs. Now, I don't want to bash ISCO unnecessarily, so I kind of want to highlight a lot of folks say that, you know, we implemented ISCO and it failed. Like I said before, it's very rare that the chemistry fails. It's typically that it just wasn't applicable. This is evidence of improvement via ISCO. So this is a well from that same site that we just discussed, a different well that demonstrated even better treatment during the injection phase. So same setup on the plot. You can see during the green line injection phase, there was a considerable reduction in BTEX concentrations, only to be frustratingly rebounded to at or above pre-injection concentrations. But if we look at another plot of this data where we look at the ratio of benzene and toluene to ethylbenzene and xylenes, we do see a definitive change. Now, why would we look at benzene and toluene versus ethylbenzene and xylenes? Benzene and toluene are going to represent the lower molecular weight, more soluble, less likely to absorb constituents of this petroleum hydrocarbon consortia, whereas ethylbenzene and xylene are heavier, slightly lower solubility, and more likely to absorb. And if we look at the ratio of these two together, pre and post injection, there's a definitive sustained reduction in the risk and toxicity profile of this contamination. So even though the concentrations remain, if you're within the confines of a risk evaluation system, this can be a way of looking at your data to demonstrate that positive measures were taken, even though the net result is that your total BTEX concentration didn't drop. Always like to end on a positive. So this is a sweet spot implementation for ISCO. It's particular to a trichloroethene TCE site that was in New York State. ISCO was used as a polishing technology following a large source removal. So the source removal shown is the black rectangle. The bulk of the source, which was a leaky sewer pipe, was removed, as well as considerable soil around it. There was an ISCO lab scale study that demonstrated alkaline activated sodium persulfate could persist for up to 30 days in situ. And because the groundwater velocity was around a foot per day, if implemented appropriately, these ISCO could be implemented in transects. Now that's novel because we typically think that ISCO, we have to bring the reagent in contact with the contaminant. And if we're using an oxidant like catalyzed hydrogen peroxide, which has a really low persistence, and implementing ISCO in transects is going to be less effective. But in this particular instance, because the natural oxidant demand or the interactions of alkaline activated persulfate with the natural geochemistry was such that we could persist meaningful persulfate concentrations for 30-plus days, we were able to design it in transect orientation. And after one large-scale injection across the site, 2 years later, there was only 2 monitoring wells where the concentrations had rebounded to above the then MCL for TCE at in New York with 5 micrograms per liter. And I'd point out that at 2 locations, which I'm showing here and here, there were monitoring wells down gradient of the transects to monitor the persulfate concentration as well as treatment. So we were able to confirm the distribution in the field, and ultimately this achieved a regulatory endpoint. And it's important to highlight that this is an implementation of ISCO in a sweet spot because it was implemented alongside a source zone strategy. There was focus on achieving meaningful distribution. There was an implementation over the full dissolved phase plume. And it was completed within a regulatory framework that allowed some flexibility with respect to the end game. So to summarize, the applicability of chemical treatment specifically for an LNAPL source zone is really a pyramid that's built upon the site characterization and the LNAPL CSM that Rick had laid out at the start of this, and that the nature and extent of the contamination that remains can completely preclude chemical treatment as an option or dictate its implementation, whether it has to be in situ mixed because the source mass is just so, there's a lot of source mass in really low permeable environment. The second part of that pyramid is a robust design, understanding the injection volumes, the reagent contaminant contact, and the chemistries, the geochemistry, treatability studies for proof of concept, and the like. And then lastly, when it comes to implementation, safe and complete execution. We deal with some dangerous chemicals with ISCO, strong acids, strong bases, strong oxidants, strong reductants. So it's very important that we minimize the worker interaction with these chemicals to the extent practical. And then once we mobilize to the field, we take the time to do it right. We achieve the dose response that we need to achieve. We're in communication with regulators and stakeholders that, hey, you know, we're approaching our planned injection volume and we still haven't seen breakthrough. We might need to exceed that volume, and here are the reasons why, and here's a plan to monitor for potential secondary effects. So with that, I'm going to hand it back to Rick now to talk about some strategies that may be applicable when ISCO's not.
All right, thanks, Jeff. And I'll finish up really quickly so we'll have some time for some questions. So if ISCO isn't effective and you're in a situation where there is a composition risk, as I discussed earlier, what can we do? Well, natural source zone depletion should be something we're all thinking about now. We've always known that LNAPL weathers. We've got measurements of the rates now, and it goes at hundreds to thousands of gallons per acre per year for a broad range of petroleum hydrocarbons. It acts on the entire LNAPL body, and it's effective for all types of LNAPLs. If we need to get a little more aggressive, we can enhance natural source zone depletion. We can add oxygen through air, either by biosparging or by bioventing. We can also add other electron acceptors, this anaerobic biooxidation, either through, say, surface application of nitrate or injection of Epsom salts. I'd caution that injecting these same chemicals is going to face a lot of the same challenges as Jeff just discussed with ISCO. You got to think about the stoichiometry. You've got to think about the delivery of those. So when you're thinking about enhancing NSCD, one of the first thoughts should just be to enhance the aerobic degradation that's going on. If you want to get even more aggressive than that, and there's a volatile fraction to your LNAPL, then we step into some of the traditional remedies like air sparging and soil vapor extraction, or dual phase extraction, also known as dewatering and SVE. Here you're pulling the groundwater down below that NAPL zone to let the air flow through the NAPL zone and volatilize the NAPL and enhance aerobic degradation, or you're bubbling air up through the NAPL zone to do the same thing. These techniques can have very high initial mass reductions, but typically you see them fall off within half a year to a couple of years. And then you're back to essentially a bioventing or biosparging system. If we need to get even more aggressive than that, heating technologies are a phase change approach that can be applicable for even low volatility LNAPLs, where we're heating up the subsurface, we're heating up the LNAPL so that the vapor pressure of the LNAPL increases and you're able to extract it in the vapor phase. Again, you can have fast depletion of the LNAPL itself as well as the high volatility fraction of the LNAPL. So with that, just some reminders of what other phase change technologies are available and how aggressive we can get with them. I want to summarize what we've talked about, starting with thinking about your LNAPL site from a risk-based LNAPL management approach. What are the goals that you want to achieve for the site, and how do they relate to where the LNAPL is in the subsurface? Do you have a migration risk? And I'd say at most sites we don't, because migration risks really are only present very soon after release. For the most part, then we're looking at composition risk and how can we change the mass and change the composition of the LNAPL in order to get to our remedial goals. Use an LCSM to help you decide what those concerns are, go back to your LCSM to help you decide what sort of remedies you can use to address those concerns and reach those goals. Improve the LCSM yet again to help you design your remedy or control, and to measure the performance. Think about phase change technologies, whether it's ISCO or one of the other phase change technologies I just talked about. They are applicable to all states of LNAPL. Whether you've got LNAPL in wells or not, you can use a phase change technology to achieve composition risk reduction. And last, there's a reason that we return again and again to the old reliable phase change technologies, whether it's bioventing, whether it's air sparge SVE, whether it's multi-phase extraction. These all act in a dominantly phase change way or completely phase change way. And even if it's just letting a site weather out on its own and let nature reduce the risk, we really understand a lot more about how the source zone naturally depletes now, so that we can have confidence that that is going to continue into the future and it will get to an endpoint. So last, I'll just say that there's the ITRC team that's been around for about 10 years now. We've done a lot of LNAPL training, classroom trainings, internet-based trainings. There's the guidance document, and a lot of states have adopted the framework that is more or less what I discussed here for approaching LNAPL sites. So, use that guidance document, refer to that guidance document. There's going to be a new guidance document coming out the next year or so. So look forward to that. So with that, I apparently can't go to the next